Hi everyone. In this video I'm going to show you how to sketch the root locus for a given system for an example that we have here, and then how to analyze the stability of the closed loop system accordingly. So here we have the example provided for us in terms of the transfer function, having the GP or the process transfer function equal to s squared plus 4s plus 8 over s squared times s plus 2. And we assume that the controller here, so the GC of S is equal to K, or it's a proportional controller. And we want to sketch the root locus plot for this system. So let's start by determining the order of the numerator and denominator for this system. We have n equal to 3 because we have 3 poles, and we have m equal to 2 because we have 2 zeros for our L of S, or for the open loop system. As a result, we have R equal to n minus m, which is equal to 1, and 1 is the number of asymptotes. So this means that our root locus will have 3 branches. 2 of those branches will go towards the 2 zeros that we have here, and 1 branch will go towards infinity using 1 asymptote. We have 1 asymptote. For that we can find out xa. So xa, or the point of abscissa, is the point in which the asymptote crosses the real axis. But since here we have only 1 asymptote, indeed it will not be important. It will be, you can think of any point on the real axis. Yeah. In any case, you can find it in this way. So r times xa, where r is equal to 1 in this case, will be equal to sum of zi's minus sum of pi's. Let's determine where are the poles and zeros located for the system. Here we have the real axis, imaginary axis, and here we have the location for the poles, 2 poles at the origin, 1 pole at -2. And regarding the zeros, we have the zeros located at these points. So plus -2 plus 2j and -2 minus 2j. And if you put them here in terms of the so let me maybe write it here. Xa will be equal to sum of zi's. So the real part of the z's will be added to each other. We will have z1 is equal to 2 plus 2j, and z2 is equal to 2 minus 2j. So as a result, we will have 2 plus 2 for the zi's, minus for the pi's, we will have 2 here, and we have 0 plus 0 over r, which is equal to 1. Or in other terms, we can write the transfer function in this way. gp1 of s could be rewritten in this format: s squared times s plus 2, and as the denominator we can write s plus 2 plus 2j times s plus 2 minus 2j. So here we have z1, we have z2, p1, p2, and here we have p3. Therefore, we will have xa equal to 4 minus 2 over 1, which will be equal to 2. And for the angle of the asymptote KCA, we have 2h plus 1 over r for the positive locus, and 2h over r for the negative locus. Again, r is equal to 1. As a result, the KCA will be equal to, replacing h with 0, we will have, here we have times pi. We will have pi for the positive locus, and we will have 0 for the negative locus. Now we can draw the asymptote. Maybe let's prepare two separate graphs, one for the positive locus with the real and imaginary axis, and one for the negative locus with the real and imaginary axis. Let's determine the location for the open loop pose at -2. We have the pose, and we have zeros here at -2 plus 2j minus 2 minus 2j, and the same for the negative locus. In terms of the asymptote, we can draw it. So we will start from point 2, somewhere here, and we will have angle equal to pi for the positive locus. So this will be the asymptote for the positive locus. And for the negative locus, we will have the point xa here, and the angle for the asymptote is equal to 0. So this will be the asymptote for the negative locus. As the next step, we can think of the sections of the real axis which belong to our root locus. So looking at the location of the poles and zeros, we will have these three sections indeed, from -infinity to -2, from -2 until 0, and from 0 till +infinity. We can count the number of poles and zeros on the left-hand side of this region. For the first case, we see that we have so 2 zeros, one pole at -2 and 2 poles at the origin. And in general, we have 2 zeros, 3 poles, or we have 2 zeros plus 3 poles, which is equal to 5. For the region between -2 and 0, for this region, we have only 2 zeros on the two poles on the right hand side. So we have the number of poles and zeros equal to 2. And for the region from 0 towards +infinity, we have nothing, 0 poles and zeros. So we have 0 here. And from these three, only the first one is an odd number. So this region belongs to the positive locus, and these two belong to the negative locus. Or in other terms, from -infinity to -2 belongs to the positive locus, and from -2 till infinity belongs to the negative locus. And we can determine these regions on the plots. So let me just remove these highlights here. From -infinity to -2 belongs to the positive locus. So this is what we have. And from -2 until +infinity belongs to the negative locus. So this is what we have in terms of the real axis. So for now, we have the real axis and we have the asymptotes. Now, as the next step, we can think about the break-in or break-away points that we may have for this case, for this example. So we know that in order to find out the break-in or break-away point, we need to find the roots for d rho over ds equal to 0. And this is equivalent to, as you should already know, it's equal to m prime d minus d prime n equal to 0. We have n of s equal to s squared plus 4s plus 8, and we have d of s equal to s squared times s plus 2. So this comes from the transfer function that we have for our system. As a result, here we will have m prime equal to 2s plus 4 and d prime equal to 3s squared plus 4s. Plugging these into the equation here, we will get 2 times s plus 2 or 2s plus 4 times d, which is s squared times s plus 2, minus d prime, which is s times 3s plus 4 times n, which is s squared plus 4s plus 8, equal to 0. By looking at this, we will get s equal to 0 as one of the roots. So this s from here and the power of 1 power from the s here will be cancelled. We have s equal to 0 as one of the roots of the d rho to ds equal to 0. And what remains for us is 2s times s plus 2 squared minus 3s plus 4 times s squared plus 4s plus 8 equal to 0. We need to find out the roots for this equation. I think you can do it yourself, either maybe analytically or using some tools like MATLAB. But what you will get at the end will be, so I call this S1, you will get a real root, which is around minus 1.41. And you will get S3 and 4, they will be some complex values, which are not acceptable for us as the break-in or breakaway point. So we see that in general, we will have 2 points, S1 and S2, at origin and at minus 1.41 as the break-in or breakaway points. And we need to determine which one belongs to the positive locus or negative locus. So again, going back here and having a look at our initial plots for the root locus, we see that the point minus 1.41, this point here, we can see that it for sure belongs to the negative locus. Why? Because it's somewhere here, minus 1.41. So that means that this belongs to negative locus. And we can also determine whether it's a break-in or breakaway point. However, by looking at the diagram here, I can say that it will be for sure a breakaway point. Why? Because I know that this pole here will move towards plus infinity on the real axis, and at this point it will break away from the real axis. So this is a breakaway point. The other way to determine whether it's a breakaway or break-in point is to find out the second derivative of rho with respect to s, evaluate it at s2 minus 1.41, and determine the sign, whether it's bigger than 0 or smaller than 0. Then you will know whether it's you will know that it's a breakaway point. Regarding s1 equal to 0, it could belong to negative locus or positive locus because both of them have poles at the origin. But again, by looking at here, I can see that since the area around s equal to 0 doesn't belong to the positive locus, the poles at the origin would need to depart from the real axis for sure. So it's, and that means that we will have a breakaway point at origin for the positive locus. On the other hand, for the negative locus, we have 2 poles at the origin, and since the area around the origin belongs to the negative locus on the real axis, each pole will start to move on the real axis, or each branch will start to move on the real axis. So as a result, here we will have S1 equal to 0 as a breakaway point. So what's the next step? The next step is to determine or to find out the angles of departure and angles of arrival for the zeros and for the poles. In the case of negative locus, we need to find only the angles of arrival for these two zeros, and we don't need to find the angle of departure for the poles at the origin, because as I already mentioned, the branches will move or they will stay on the real axis. So we already have angle of departure from the pole equal to 0 and pi for the poles at the origin for the negative locus. However, for the positive locus, we don't know what will be the values, and we need to find it out. And so we need to find out the angle of departure for the poles at the origin and angle of arrival for the complex zeros that we have. And here we need to find out the beta arrival or angle of arrival. So let's see how can we find it out. So this is our next step. Let's start with the angle of departure, or alpha departure. Since we have two poles, we have q times alpha departure. Since we have two poles, we have two alpha departure at the origin, which could be found out as sum of phi i's minus sum of theta i's plus 2h plus 1 times pi for the positive locus. And for negative locus, even though we don't need, but we can try to verify this. So let's see how can we find out the phi I and theta i's in this case. I will draw the location of poles and zeros here again. We have two poles here, one pole at -2 and two zeros at -2 plus 2j and -2 minus 2j. To find out the phi i's and theta i's, we need to draw a line from each one of the poles and zeros to the origin, because we want to find out the angle of departure here for the poles at the origin, and then we will find out phi i's and theta i's. For theta I, we have only one pole which is not in the origin. So to find the angle of this pole with the origin, we need to connect that pole to the origin. We need to draw a line from this pole towards infinity and then find out the angle between these two lines, which, as you can see here, is equal to 0. For the zeros, on the other hand, again, we need to connect the 0 to the pole here. We need to draw a line from 0 towards infinity, and we have to find out this angle here, which is phi 1. And for the second 0 as well, we connect it to the origin. We draw a line from the 0 towards the origin, towards the plus infinity, and we find this angle, which is phi 2. So since here we have the values, here we have 2 in terms of the amplitude or the value, and here we have 2 as well. As a result, this angle will be equal to 45 degrees. And the same thing here, we have 2 here, we have 2 here, and this angle phi 2 will be equal to 45 degrees. Since we have 45 degree here, phi 1 will be equal to 180 minus 45, which is 135. And phi 2 is equal to 45. So now we have everything here. We can write 2 times alpha departure is equal to sum of phi i's, 135 plus 45, minus sum of theta i's, 0, plus 2h plus 1 times pi for the positive locus, and the same thing. So 135 plus 45 is 180. Yes, 100. Okay, I think I just made a mistake here. Instead of 180, we have 360 minus 45, which will provide us 115. As a result, we have 315 plus 45, and here we have 315 plus 45, which is 360, minus 0 plus 2h pi for the negative locus. So 2 times alpha departure could be obtained by setting values for h equal to 0 and 1, because we have two poles. We will have, so 360 plus setting h equal to 0, or we will have 2 pi plus h equal to 0, we will have pi, and we will have 2 pi plus 3 pi. Here we will have 2 pi plus 0 and 2 pi plus 2 pi for positive locus, for negative locus. And finally, we have 2 plus, we will have 3 pi over 2, and we will have 5 pi over 2 for the positive locus. We will have pi and 2 pi for the negative locus. So these are the departure angles. Let's see how we can use them in our root locus plot. For the positive locus, we will have 3 pi over 2 and 5 pi over 2. 5 pi over 2 is indeed equal to pi over 2. So for here, we will have 3 pi over 2 and pi over 2 as the departure angles from for the poles at the origin. So let's come back here. We will have one of the poles departing from the angle of pi over 2 and the other one departing with the angle of 3 pi over 2. For the negative locus, on the other hand, we have pi and 2 pi, or 2 pi is equal to 0 as well. So we will have pi and 0 for the angles of departure. And that's what I already have mentioned. Yeah, we have the poles departing from the branches departing from the poles with the angle of pi and 0, as we can see here. So next thing to consider is to find out the angle of arrival at the zeros. So angle of arrival, and we have q times beta arrival equal to minus sum of phi i's plus sum of theta i's plus 2h plus 1 times pi for the positive locus, and minus sum of phi i's plus sum of theta i's plus 2h pi for the negative locus. And let's see how we can find out the value for phi i's and theta i's. We have two poles here at the origin, one pole at minus 2 and two zeros at minus 2 plus 2j and minus 2 minus 2j. If I want to find the angle of departure for the angle of arrival for the 0 here, let's see what do we have in terms of the angles coming from the zeros and the poles. Let's assume first this 0 here. So I need to connect this 0 to the 0 at minus 2 minus 2j and draw a line from here towards plus infinity and find out this angle, and it's obviously equal to 90 degrees or pi over 2. So we see that we have phi 1 equal to pi over 2. The angle coming from the poles, we have one pole here, connecting it to the 0, drawing a line from that pole towards the infinity, we will have this angle, which is again equal to pi over 2. So theta 1 is equal to pi over 2. And we have two zeros here, theta 2 and theta 3. And the angle coming from them is equal to this angle, which is pi over 2 plus pi over 4, or 3 pi over 4. So that will provide us the angle of arrival at the 0 by plugging these values into what we have here. So we can rewrite this here again, minus pi over 2 plus sum of theta i's, pi over 2 plus 2 times 3 pi over 4 plus 2h plus 1 pi for the positive locus, and the same terms minus pi over 2 plus pi over 2 plus 2 times 3 pi over 2, which is indeed 3 pi over 2 plus 2h pi for the negative locus. Q is equal to 1 because we have only one zero here. So beta arrival will be equal to minus pi over 2 plus pi over 2 will be cancelled with each other. H will be equal to 0 only because we have only one zero. As a result, we will get arrival beta equal to 3 pi over 2 plus pi for the positive locus and 3 pi over 2 plus 0 for the negative locus. Finally, we have arrival angle equal to, so 3 pi over 2 plus pi will be equal to 5 pi over 2, or in other words, it will be equal to pi over 2, and 3 pi over 2 for the negative locus. So for the positive locus, we have angle of arrival equal to pi over 2. For negative locus, we have 3 pi over 2. Let's go back to the original plot that we have here. Angle of arrival for this 0 will be equal to pi over 2. And for this 0, it will be equal to 3 pi over 2, or minus pi over 2. And since we need to have the symmetry, we will have 3 pi over 2 for the angle of arrival for this 0 here for the positive locus. And for the 0 in the negative locus, we will have angle of arrival equal to pi over 2 because we need to have the symmetry. So now we can indeed finish the root locus diagram for this system. So having a look at the branch which starts from this pole at -2 for the positive locus, we know that it will remain on this real axis. It will go towards -infinity. And two branches originating from the origin, they will go towards the zeros, the complex zeros that we have here, and they will arrive at the angle of pi over 2 and with the angle of minus pi over 2. So this is what we have for the positive locus. In the case of negative locus, one branch will start from the pole at the origin. It will go towards +infinity on the real axis. The other branch will come towards the other pole. They will depart at this point, which we already have obtained the value for that. It is -1.41. Then they will depart the real axis and they will move towards the zeros, and they will arrive at the zeros with the angles that we already have found. So therefore, this will be the overall root locus for this system, as you can see. And now we can discuss about the stability of the system for different values of k. For positive locus, where we have k between 0 and infinity, we see that for all the values of k, the closed loop pose will be on the left-hand side. As a result, for this situation, our system will be, the closed loop system will be stable. On the other hand, for the negative locus, we can see that for any value of k between -infinity and 0, we have one pole on the right hand side, and as a result, the closed loop system will be unstable all the time for these values of k. Now let's just check the result on MATLAB as well, and compare it with what we have obtained here. So I already have declared the transfer function g, and with this our locus comment, we will be able to see the positive locus for the system. So you can compare it with what we have. As you can see here, the angle of arrivals at the zeros and the angle of departures from the poles are consistent with what we have here. And one of the branches will go from the pole at -2 towards -infinity. Let's see what we have for the negative locus. And this is what we get. Again, you can compare it with what we have obtained for the negative locus, and you can see that the angle of Arrivals at the zeros, angle of departures from the pose and sections of the real axis, which belong to the root locus, are consistent with what we have obtained. Okay, so I think we are done for this video. There's nothing else to consider here. We have determined the values of k for which the closed loop system is stable. So I hope you have enjoyed watching this video and you have learned how to especially calculate the angles of arrival and angles of departures from the pose and the angle of arrivals at the zeros. So thanks a lot for watching again, and see you next time.